Hi everybody, happy Wednesday. Remember that Friday we don't have class. Today we're discussing Stewart section 3.3, which is derivatives of logarithmic functions and exponential functions. Before I start discussing that, I want to remark on two things that were common mistakes on the quiz. First of all, the symbol for the derivative of something is d dx of that thing. So the derivative of blah is d dx of blah. It's not dy dx of blah. So a lot of you think that the symbol for taking the derivative of something is dy dx of that thing, but it's not. If you're taking the derivative of something called y, then yeah, you do get dy dx, because you put a d dx in front of a y and you get a dy dx. But if you're taking the derivative of anything else, it's not dy dx of that thing. So the very first problem, that's very important, because the first problem on the quiz involved implicit differentiation. Now at some point in that problem, a dy dx is supposed to show up, but it's not at the beginning when you are just taking the derivative of both sides. So that's the first comment. The second comment is about canceling before multiplying. Now for that, I'm going to turn off the lights. In general, I find students always want to multiply stuff out instead of keeping an eye out for things that can be canceled. So on this particular quiz, so actually I have scans of a previous quiz from a previous semester. The problem was slightly different, but it was still a related rates problem involving a right triangle. So what I've got here is I've got a bunch of student solutions that have an unfortunate amount of work on them, but they miraculously ended up with the right answer. What I have not shown is far more student solutions where they did this kind of unfortunate work and then ended up making mistakes because it makes the work more dangerous. So the idea is you have the Pythagorean theorem, you take the derivative of both sides, and you get this: 2a, a prime, 2b, b prime, 2c, c prime. And look, those green 2's, they could all cancel right here, right now. But this student didn't cancel them. Drag them out. 2, 2, 2. Oh, multiplied 2 times 5. So you had 10, 24, and all those 2's, all the way to the end. They lost a point because they didn't simplify. They didn't cancel. So they made their work much harder by dragging all these 2's through. And in the end, they lost a point because they made their work so hard they didn't even notice that they had not canceled fully. Now look at the next paper. This person ended up with the right answer, but again, look, 2, 2, 2. Those 2's could have canceled right then. But instead, this person wrote 1, 2, 3, 4, 5, 6, 7, 8, 9, all these steps with all these extra 2's in them that were completely unnecessary. And I've seen this, hundreds of times. And what happens is students will sometimes, and look, suddenly you're dealing with 24 and 10 and, the harder numbers because you didn't cancel the 2's. And I've seen many times where students will drag all these extra numbers through, and because you're writing down so many more numbers, your paper's more cluttered, you're busy writing more symbols, and you're prone to make mistakes. So a heartbreaking number of students will do this kind of thing, and then because of all these damn 2's, they'll make a mistake. So keep your eye out for things that can be canceled. Cancel them right then, right where they first appear. As I said, this is on the web page. All these pages are the same thing. A green line where all those 2's could have canceled, but they didn't cancel, and they had to write all those 2's. So cancel before multiplying. Okie doke. So meeting part 2 is derivatives of logarithmic functions. So there are 3 new rules, and I'm going to write them down. I don't generally like to write down rules that are in the book, but it's important, I think, to write them down because the book saves a little bit of ink by writing these rules down in a way that saves some ink, but they obscure a really important fact. I've mentioned a few times that I don't remember much from my freshman year of calculus, but I remember some things that were confusing, really mysterious, and one of them has to do with these derivative rules for logarithm and the way that they're presented. So here's the first one. So the natural logarithm rule says that the derivative of ln of x is 1 over x. Now, here's where I write something that the book does not write. 1 over x restricted to x greater than 0. If you don't write this, it's actually not really correct. And then the derivative of ln of absolute value of x is 1 over x. That's not restricted. And then the derivative of log base b of x is 1 over x, again, but also with ln of b in the denominator. And this is restricted. So I'm going to get to what this means in a minute. I'll tell you that the proof of this is beautiful. It's in the book. So I'm going to say, see the book for beautiful proof of star. So I'm not going to prove it, but I do want to discuss why we should believe it. So why is that rule believable? Well, we should make a graph of ln of x. That's going to be our function. And we should make a graph of 1 over x restricted. That's going to be the derivative. So we have our f of x equals ln of x. And that's going to be up here, and that's going to look like this. And then we have down here, we have f prime of x is 1 over x, but restricted to x greater than 0. So this graph looks like this. If I didn't restrict it, there'd be a left side on this graph. That's the key thing. So this, what we're looking at, is the 1 over x function, but just the right side of it. Now let's think about why this derivative rule makes sense. Let's think about what we'll do what we always do. Let's pin some tangent lines on this graph. There's a tangent line, there's a tangent line, and there is a tangent line. And let's think about those slopes. Here the slope m is large and positive. Here the slope m is medium, positive. And here the slope m is a small positive number. Well, now let's look at this graph and look at the y values. Here, y is large, positive. Here, y is medium and positive. And out here, y is small and positive. So it seems like the numbers that are the slopes on this graph are the numbers that are the y values down here. So this rule is believable. Now, why is this rule believable? Well, basically, let me just draw it. I'm just going to draw the graphs and not the tangent line. So the graph of g of x is ln of absolute value of x. That's going to look just like that graph, but it's also going to have a mirror image. And if we draw g prime, g prime is 1 over x, and it's not restricted. There is a left side on this graph. So what's confusing in the book is the book says the derivative of ln of x is 1 over x. And then the book says the derivative of this is also 1 over x. There's no explanation of why do these two different functions have the same derivative. Well, it turns out they don't. They don't really have the same derivative. The derivative of ln of x is 1 over x restricted to x greater than 0. Now, we get sloppy with this. We often just say the derivative of ln of x is 1 over x, yada, yada, yada. But the thing is, this is going to come back later, and this is that thing that I just remember was mysterious. When it comes back later, the thing later is really weird if you have not seen this rule first. Now, let me point out something. I've mentioned this before. This is a true statement. And again, what we'll often end up just saying is that the derivative of ln of x is 1 over x. It's okay. The idea of writing it this way is, on the left I've got a function whose domain is all x is greater than 0. So we're going to be talking about the derivative just as it pertains to x is greater than 0. And so on that part of the real number line, we're looking at that part of this graph. So I guess that's why the book leaves off that extra phrase. But this is not true. ln of x equals 1 over x. I've seen that written on thousands of papers over the years. Thousands. I've been teaching, quite a bit longer than you've been alive. So this is just not true. And I mentioned this a couple of weeks ago when I was talking about derivative notation and writing things that are true and not true. Some of your other derivative rules, like, you know that x squared is not equal to 2x. Because you know what the graph of x squared looks like. You know what the graph of 2x looks like. You know those are not the same graph. But a lot of you probably don't remember what the graph of ln of x looks like, and a lot of you probably don't remember what the graph of 1 over x looks like. So if you write this, it's not going to set off alarm bells in your brain, because these are both strange things. But the thing is, this is not true. You can see the ln of x function is not the same as the 1 over x function. But trust me, if you write this over and over and over again, you'll start to believe it. And I've seen thousands of papers where this is true, and I've seen thousands of papers where students will in the middle of some calculation where there's an ln of x, they'll just replace it with a 1 over x, as if it's the same thing. Or there's an ln of x, they'll just replace it with a 1 over x, because students will get to think that these two things are interchangeable because they've written this so many times. So don't write this. If you want to remind yourself of the derivative rule, write the whole rule. Trust me, it's worth it. It's only a little bit of ink. Okay, so we've got these 3 rules. Let's go do some examples. So example 1. Find the derivative of ln of x squared minus 3x plus 17. Okay, so I'm going to have that function, ln of x squared minus 3x plus 17, and I'm going to just write in front of it the d dx symbol. D dx, not dy dx. I'm just taking the derivative of this thing. Now, that's a nested function. So the chain rule says that what I need to do is go get outer prime parentheses inner times inner prime. So let's do the chain rule details over here. So my inner function is x squared minus 3x plus 17. So who can help me out here? What's my inner prime? (2x minus 3). Now, here's something that, here's where the empty function business that I've been doing this semester starts to really pay off. What is the outer function? Well, by itself, that's nothing. I mean, of
whatever's inside parentheses.
Natural log of parentheses. That's the key. This, you can't just, that symbol cannot live by itself. That has to have an argument. So in this case, it's natural log of parentheses. So what's outer prime? Somebody else. What is outer prime, also written as an empty function? Well, there's no x here. Yeah, 1 over parentheses, yeah. So if your function is ln of x, then its derivative is 1 over x. If your function is ln of z, then your function is 1 over z. If your function is ln of parentheses, then its derivative is 1 over parentheses. That's really key. There is no ln of x here, and there is no 1 over x here. That's, again, this is where the empty function business really pays off. So I have to go get those parts. I have to get my outer prime, which is 1 over parentheses, and I have to stuff it with my original inner function. And then I have to multiply it by the inner function, by inner prime, keeping in mind that I've got to put that thing in parentheses, and I've got to put it up on the baseline, not on the floor. If I wanted to, I could tidy this up. This would be 2x minus 3 over x squared minus 3x plus 17. So again, there is no 1 over x here. There was no ln of x. There is no 1 over x. Now notice what we just took the derivative of is ln with a function inside. So for my second example, I want to do a more general version of that. Find the derivative of ln of f of x, where I don't tell you what the thing is on the inside. Well, I'm going to write down that function, ln of f of x, and I'm going to put in front of it the derivative symbol, which again is just d dx. It's not dy dx. And then I'm going to remind myself that this is a chain rule problem. Now I have a function inside of another function. So I'm going to have outer prime parentheses inner times my inner prime. So that's the chain rule. And let's do the chain rule details. So my inner function is f of x. So my inner prime is f prime of x. My outer function is empty. It's ln of parentheses as before. So my outer prime is also empty, and it's 1 over parentheses. So when I assemble all those parts, I get 1 over parentheses. That's my outer prime. I've got to stuff them with the original inner function, and then I've got to multiply by inner prime. If I want to clean this up, I get f prime of x over f of x. It's kind of a cool problem. It just, I would call this abstract because I'm not telling you concretely what f of x is. But notice, this is exactly what we ended up with over there. Example 3. Find the derivative of f of x equals ln of, everybody buckled in? The cube root of x squared minus 3x plus 17 divided by, gets worse, x squared plus 5 to the 3/5. Holy cow. So look at that. I've got a function inside of a function, so chain rule. The function inside is a quotient, so chain rule and quotient rule. Oh, in the numerator, that quotient, there's a function inside of a function, so there's another chain rule there. And in the denominator, there's another function inside of a function. So it looks just awful. Yeah?
Instead of doing the quotient rule, can't you split it up into 2 different things?
Dang it, Emily, you just stole my thunder. Yeah. That's what we're going to see. So I'm going to get to what Emily said in just a second. So if you look at this, it looks like chain rule 3 times and quotient rule. So there's nothing illegal about that if you do it carefully. You know, turn off your phone, turn off the TV, lock the doors, put the cat out. You can do this, but it's really unlikely that you'll get through it without making a mistake. And there's almost no way you would get through this well, it'll take a long time. So the easier way is to do what Emily said, which is postpone doing the derivative. Rewrite the function first. So we're going to rewrite f of x first using rules of logarithms. So we're not doing the derivative now, we're just rewriting. So f of x is ln of that thing, the cube root of x squared minus 3x plus 17 divided by x squared plus 5 to the 3/5. So Emily, you want to help me out here? What do we do first?
It'd be like ln of the numerator minus ln of the denominator.
Fantastic. So here we do ln of the numerator, just what Emily said, ln of x squared minus 3x plus 17 minus ln of the denominator, x squared plus 5 to the 3/5. And so the rule that we use there is the rule of logarithms. Ln of a over b equals ln of a minus ln of b. All right, what now? It still looks like a triple chain rule problem. I've got a function inside of a function inside of a function. I've got a function inside of a function inside of a function. It looks like a double triple chain rule problem. Well, remember this rule of logarithms. What is this? Don't tell me there's something that I remember from high school that you don't. This is one thing I remember from high school. Yeah.
Don't you say what's on the other side of the equal sign?
Yeah.
Is it b times ln of a?
You can't ask me, you got to tell me. You can ask your friends, but you can't ask me. Is he right? It is right. B ln of a. Excellent. So some of these things, you recognize them when you see them. So if I do that applied to this, notice this is all this stuff to the 1/3 power. So this is going to be 1/3 times ln of x squared minus 3x plus 17 minus 3/5 ln of x squared plus 5. So we use the rules of logarithms twice. Now realize that we can find the derivative very simply using this. We have logarithm of a simple function. I'm going to have the 1/3 out front, and then I'm going to have that function on the bottom, x squared minus 3x plus 17, and its derivative on top, 2x minus 3. And over here, I'm going to have minus 3/5. That function is going to be on the bottom, and its derivative is going to be on the top, 2x. That's using the result of example 2. Isn't that cool? So knowing to take your suggestion and rewrite the logarithm, and to take your suggestion and rewrite the other logarithm, you get this into a form that you can use this cool rule. That was example 3. Now that's f of x. Notice f of x looks really bad. It's all this junk inside of a logarithm. Now, example 4. Find the derivative of this function, g of x, which doesn't look so bad, is the last one. It's the cube root thing, cube root of x squared minus 3x plus 17, divided by the other term, x squared plus 5 to the 3/2, but it's not wrapped in a logarithm. But the thing is, if you look at this, it still looks terrible because it's a quotient rule and 2 chain rules. So quotient rule and the chain rule twice. So you do a trick that's called logarithmic differentiation. Hardest thing about it is not slurring that. I've had enough coffee to make me slur that. So instead, do a trick. So logarithmic differentiation. Start with g of x equals stuff. Now, take natural logarithm of both sides. So that's going to be ln of g of x equals ln of stuff. Then take the derivative of both sides. So I write d over dx, not dy dx. I do d dx of ln of g of x equals d dx of ln of stuff. Seems like I've made things worse, but you're going to see that I didn't. Because look, the derivative of ln of g of x is just like this. On the left side, we're going to get g prime over g. So g prime of x over g of x equals the derivative of ln of all that stuff. So here we used example 2. To go from here to here. Now, look, there's g prime. We're after g prime. So we're going to solve this equation for g prime by just multiplying both sides by g. So we're going to solve this equation for g prime by multiplying both sides of that equation by g. So I end up with this, g prime of x equals g of x times the derivative of ln of all that stuff. This all looks very abstract, but that's what we get from this technique that's called logarithmic differentiation. And it's a trick. All of this stuff is the technique of logarithmic differentiation. Okay, so let's apply that to this result, to this function. So we're going to apply this to our function g of x over here. That's our function. So I get g prime of x equals g of x. Okay, so all that stuff, cube root of x squared minus 3x plus 17 divided by x squared plus 5 to the 3/5 times, oh, this is going to be terrible, the derivative of all that stuff. Oh, I'm sorry, derivative of ln of all that stuff. Sorry, ln of all that stuff. The cube root of x squared minus 3x plus 17 on top. X squared plus 5 to the 3/2 on bottom, and the logarithm of all that stuff, and then take the derivative of all that stuff. But that's exactly the problem that we just did. The previous example, we took the derivative of this, and we got this. So we're going to use the result of example 3 So all this stuff is going to be out front. The cube root of x squared minus 3x plus 17 divided by x squared plus 5 to the 3/5 times that stuff. Now I want to be honest here and actually write all this junk out because I just do. So 1/3 of 2x minus 3 over x squared minus 3x plus 17. And then I have minus 3/5 times 2x over x squared plus 5. It looks terrible, and it is. But the thing is, it's a bunch of steps. I wouldn't call them baby steps, but I think you can see that, well, you know, I said before, this looks terrible. It looks like quotient rule and then the chain rule twice. If you use the quotient rule and the chain rule twice, you'll actually get the same result. I just find this a little bit more reliable. Okay, meeting part 3. Did my sign-in sheet make it around? Everybody sign in? Meeting part 3 is derivatives of exponential functions. So we have the exponential function rule, or sorry, the natural exponential rule. That is, I take the natural exponential, that's the exponential base e. So d dx of e to the x, it's the easiest rule ever. It's just e to the x. And then we have the general exponential rule. That's the derivative of a more general exponential b to the x. Well, you get b to the x again, but there's something else, b to the x ln of b. Now, I want to emphasize that these are derivatives of expressions that have an exponent. We've had derivatives of expressions with exponents before when we did the power rule. So I want to make sure that you contrast this and see what these are not. The power rule is for power functions. Not for exponential functions. And the power rule says that the derivative of x to the n equals nx to the n minus 1. Remember that? You bring down the exponent and you lower the exponent by 1. These things are not that. When you take the derivative of e to the x, you don't do the weird thing with the exponent. You take the derivative of b to the x, you don't do anything with the exponent. You don't bring the exponent down, you don't do this. So that's it's important to notice. Again, these are both expressions that have exponents, but you do very different things. In this case, it's a constant base variable exponent. That's an exponential function. In this case, it's a variable base and a constant exponent. That's a power function. So you do very different things. All right, example 5. Find the derivative of f of x equals cotangent of x times e to the x plus cotangent of e to the x plus e raised to the cotangent of x. So notice every one of these expressions has a cotangent involved and has an exponential function involved. But the relationships are different. So what rule do we use for this first one? Your hand is sort of up. Yeah. Oh, did you answer?
No, I thought that was covering my mouth.
Oh, but that's the closest anybody has to a raised hand. So.
F prime equals d of x, the first term plus d dx, and the second term plus
No, I'm thinking about just for this term. What do we have to apply for that term? Product rule, because it's a product of functions. So I'm going to have. So remember that the derivative. What's the derivative of cotangent of x? Let's do the easier one. What's the derivative of tangent of x? Secant squared of x. So I'm going to write secant of x squared. Now remembering that, do you remember what the derivative of this one is? It's just like it. Oh. Wonderful. Negative cosecant of x squared. Okay, so when I use the product rule, I have the derivative of the first, so minus cosecant of x squared times e to the x, plus the first function, cotangent of x, times the derivative of the second, that's e to the x. So that whole thing is what you get for the product rule. Now I'm going to have, what do I need to use here? Chain rule. And what's my outer function? Yeah. So when I do the chain rule here, I should have my outer prime, which is going to be cosecant of parentheses squared. And there's going to be a minus. And I've got to put my original function back inside. And then I've got to do times the derivative of the inner function. So there's my outer prime of inner times my inner prime. What about the other function? What do I do with this function? I think somebody whispered it. How do I find the derivative of this? Can you help me out again? Nope. It's chain rule again. Just a different outer function. This time the outer function is e to the parentheses, and the inner function is cotangent. So I have to go get my outer prime, so that's going to be e to the parentheses, and I have to put my original function back in, and then I have to multiply by my inner prime. So minus CSC of x squared. Isn't that cool? So three very different, well, these two are not so different. I'm just swapping the inner and outer roles, but they end up looking very different. Emily?
Why is that the chain rule, not the general exponential?
Here?
Yeah.
Well, because I've got a function inside of a function. So if you want, let's just do our, the general I don't have one of these things. My base is not some number b. My base is the number e for my outer function. So, where's my eraser? Let me just do the details. So my inner of x is cotangent of x. So my inner prime of x is minus cosecant of x squared. My outer is empty, and it's e to the parentheses. So my outer prime is just e to the parentheses. Does that help? And I think if you would see if you do this, the similar details over here, the inner and outer are going to swap. Example, holy cow, we're up to 6 examples. Let's let f of x equals e raised to the minus x squared minus 2x minus 1. Finally. A, find f prime of x. B, find the slope of the line tangent to the graph at x equals 0. C, find x coordinates of all points where there is a horizontal tangent. In the next 3 minutes. All right, well, I'm going to go through this in kind of a quick way. Notice I have an outer function and I have an inner function. So I'm going to be doing the chain rule. So f prime of x is going to be my, by the chain rule, it's going to be this, the derivative of the outer function, which is going to be e to the parentheses. And then I have to put the original inner function back in. And then I have to take the derivative of the inner function, so minus 2x minus 2. So that's, again, that's outer prime of inner times inner prime. Now, how do I answer B? Well, I'm being asked to find a slope. So I'm going to start by saying m. And I'm asked for the slope at the place where x equals 0. So I'm asked to find f prime parentheses 0. So that's going to be e to the minus 0 squared minus 2 times 0 minus 1 times minus 2 times 0 minus 2. So that's e to the minus 1 times a minus 2. So that's minus 2 over e. Now remember that e is like 2.7, so that's roughly minus 2/3. Now for question C, we know that 0 is the m, and that's f prime of x. We're going to solve for x. So 0 equals e to the minus x squared minus 2x minus 1 times minus 2x minus 2. So look, I've got two things being multiplied together, and I have to get 0 as a result. Now remember that e to anything is always greater than 0. So this will never be 0 because, remember, e to anything, the range of the exponential function is positive y values. So if I've got two things multiplied together and they have to give me 0, and this thing is never going to be 0, that means that this must be the thing that's 0. So this must be 0. Ooh, sorry. So I get 0 equals minus 2x minus 2. So I end up with x equals minus 1. Now, I'm going to quickly draw the graph of this function and its tangent line. This function is a famous shape. It's what's called a bell curve. At x equals 0, the slope is a negative number. But at x equals negative 1, the slope is 0. So here we found this slope at x equals 0 is minus 2 over e. And we found at this x value, at x equals negative 1, the slope is 0. All right, sorry to keep you a minute late. Thank you all.